So we are going to look at the basic mechanics that rule inference, using probability to guide us toward identifying the most sensible and best explanation to any situation. Remember that our objective is to come up with a probability density function for a given hypothesis. That can, in this case, be some parametric model that describes a given target that is a function of one or more parameters. Here, the example we're going to go back to is the example of the probability density function for the angular diameter of a star that we're going to try to deduce from interferometric observations. This probability density function really evaluates or quantifies the probability of a given theory given two things. Of course, the data that is at our disposal, and again, because it ends up being important down the end, any sort of additional implicit or background information we may have about a given situation. Now, unfortunately, there is no device that gets you to measure this probability directly. In practice, the situation is reversed. The typical situation looks something like this. You are facing a bunch of data that was acquired with some experiment, and the goal should be to estimate from that data the probability density function of your hypothesis. In practice, it's impossible because the only thing that you can really evaluate is the quality of the data itself. So somehow the probability is not going to be about your hypothesis, but about the data. You're going to go about and test some specific models, like this one here, for example, that provides a somewhat convincing description of what the cloud of points seems to indicate, but that also would make a somewhat reasonable explanation. And the only thing we can actually evaluate is the probability for that data to actually match our hypothesis. And if you notice, the two letters H and D here are reversed. We'd like to be able to invert those positions, and this is not what we can directly evaluate. In order to do so, we need to look back at the definition of what is a conditional probability. Now, that may remind you some of the mathematics you may have seen toward the end of high school. The conditional probability, or the probability of a proposition A given that a proposition B is true, is simply defined as follows. This is 17th century mathematics as the ratio between the probability that A and B are true simultaneously divided by the probability of B itself. Now, an interesting side note is that, of course, if A and B are independent events, then the probability of A given that B is true should be no different than the probability of A, regardless of the status of B. And the independence of A and B simply means that the combined probability of A and B is equal to the product of the probability of A and the probability of B. The ratio just cancels out, and you indeed verify that. If two events are independent, then P of A given B is equal to P of A. Now you can write the exact same thing, switching the order of the letters, and realize that the probability of A and B, or the probability of B and A, are of course identical, simply because multiplication happens to be commutative. And so you can combine those two expressions to come up with something that is known as Bayes' theorem, that allows you to go to reverse the order of the letters in a set of conditional probabilities. Now it doesn't quite look like yet like what we would like to look like. In addition to A and B, we also have to include the fact that we may have access to additional background information, and so we are simply going to make that more obvious by adding to the given part of those conditional probabilities any sort of background information we may have about a given situation. This is pretty much the form that we're going to use over and over when dealing with data analysis using that Bayes theorem, the Bayesian framework, if you will. Let's look at this one more time because this is really important. That Bayes theorem is made up of 4 parts. We have the end product, the one thing we'd like to be able to evaluate, which we will call the posterior probability density function. And that posterior probability depends on 3 other parameters. The one that evaluates the how my data and my model are alike is going to be my likelihood. But that likelihood is modified by a prior probability, the probability of my hypothesis given the background information, regardless of the data, so some sort of prior knowledge about the given situation. And all of this is normalized by something that is called the evidence, which is a function, a probability that in a way is like a constant because it does not depend on the hypothesis. Which means that in practice, we actually are not going to bother with that term at all. We're going to simplify it and eliminate it and replace the equality by a proportionality sign. And so we end up with the posterior probability being proportional to the likelihood and the prior probability function. Now this is a very interesting way of looking at data because data processing, because this simple equation somehow encapsulates the process by which prior knowledge, like current theories about the universe or about a given specific object, are going to be modified or confirmed by new information. This is a really powerful way of looking at the scientific method at work, really. So we have identified 2 terms. The first one was the likelihood, which typically ends up being noted like a big L here. So let's look a little bit more of what makes up that likelihood. The example we're going to play with is a fictive example about the interpretation of one single data point, which is going to be something a little dangerous to do, but for the sake of our explanation is actually going to be quite all right. We have the following interferometric observation highlighted right there in our plot. For a 40-meter baseline, we were able to measure some visibility. It happens to be somewhere around 0.3 with some uncertainty on the visibility measurement. What we would like, the hypothesis we're going to test is the hypothesis of a uniform disk star. We're going to assume, this is a very strong assumption, that the star can be modeled like a uniform disk of diameter theta, and the parameter we're going to go about pinpointing the exact value for this parameter here. Given that we model our star like a uniform disk, we can use the Van-Sittert-Zernike theorem to predict what the visibility function of that object should look like for any baseline. And we're going to see in a little bit exactly how one goes about producing such predictions using the Van-Sittert-Zernike theorem. And so we have this red curve here, which was just produced for a model of about 10 milliarc second. The 10 milliarc second diameter star would produce this visibility curve for an observation that would be carried in the K-band at 2.2 micron wavelength. So we have this data point, which is one value, one best estimated value, and one uncertainty associated to it. And if this measurement happens to be produced by the average of, dozens or hundreds, in fact, it doesn't take all that many for this to be true, but if it's the average of, say, 100 individual measurements, then we can invoke something called as the central limit theorem that allows us to pretend that the errors associated to this measurement are going to follow Gaussian statistics. In addition to this, so sigma is going to be the standard deviation of a Gaussian distribution, essentially. We also have our model, which predicts for a given diameter theta some visibility b theoretical. And so because we have Gaussian errors, this is typically what a Gaussian distribution looks like, normalized Gaussian distribution. The wider it is, the larger the standard deviation is. And this is the equation that would be the one used to quantify what's in the likelihood function for that given data point. And so we simply see that we have an exponential minus a half of the quadratic difference between our measurement and the theoretical value. And so this, which is homogeneous to a probability, in fact, it's even normalized to be exactly like probability, really evaluates how much the data point and the model actually look alike. And our goal is going to fine-tune the value of the parameter theta to ensure that we maximize this likelihood. This is what we started from, our data points, and the original visibility curve for a model for a uniform disk of 10 milliarc seconds in diameter. What we see is that we can fine-tune things a little bit to find a curve that is going to go exactly through the point, which is going to be for about 9.5 milliarc seconds. Now remember that we also have uncertainties associated to this data point, which means that there are actually several curves, several such values of theta that would make a somewhat acceptable solution for this. And so these uncertainty on the value of the visibility are going to translate into uncertainties on the value of the parameter we're going to estimate. And so in the things that follow this video, we're going to actually look at what rules the propagation of errors from one place to the next. But you see here how important it ends up to produce the observables with the smallest possible uncertainty, because they are the ones that are going to help us constrain better and better the parameters of the object we're observing. Now, all of this discussion was solely about the likelihood function, and yet I made a big point introducing Bayes' theorem about the importance of the prior. And here I'm going to show you that in some cases the prior can have a huge importance. And in this case I'm going to modify slightly the starting point, where we have a measurement that was performed for a slightly larger baseline, around 50 meters, and a visibility that is significantly lower, somewhere around 15%, between 10 and 15%. The point is highlighted right there on the screen. Now you have to realize that there in, if you look carefully at this curve, you can see that it is possible to find more than one solution that would maximize the likelihood. This one with the 10 milliarcsecond diameter is not far from being ideal, but a very different solution. Something with a 15 milliarcsecond diameter, like the one you have right now on the screen, does actually a better job than the previous one, and is a better match to our observation. This is the kind of circumstances where knowledge of prior knowledge coming from earlier observations, for example, is going to play a part. If you were to draw the likelihood function, the probability density function of theta for this observation, trying to adjust it with a uniform disk diameter model, well, this is what your distribution would actually look like. Instead of featuring only one nice Gaussian distribution, you see that it features two lobes, and one of them happens to be significantly larger than the other one and doesn't look like a Gaussian anymore, really. You have what you call a bimodal distribution here, and when facing that kind of situation, statistically, it is very hard to tell which one you should pick over the other. The two solutions are equally probable, this one and this one right there. Now, if prior observations were, for example, inconclusive, were not able to constrain the angular diameter of that given object, but we're able to put an upper limit to this diameter. Take, for example, Stephan's earlier observations of stars. Despite the fact that he was not able to resolve any object with an experimental setup of 65 centimeter aperture, he was nevertheless able to say that the angular diameter of stars had to be shorter than 158 milliarcseconds. That was his conclusion. The same sort of constraint can come from interferometric observations and tell you that for the waveband that was used, it's impossible, it's not possible, there's an upper limit on the angular diameter, which in this case happens to be somewhere around 12 milliarcseconds. When you have access to this, the probability you should use for the posterior distribution happens to be the product of the two, which is going to essentially erase the second solution. And so this is why this framework of Bayesian statistics ends up being very important in the way you go about interpreting data. And this is also why the prior you're going to choose is going to be very important. Remember that in one of our previous videos, the stories of the blind man going about the elephant made the wrong conclusion because they had a prior that was way too strong for them.